This is the molecular model kit lab, and so I'm going to show you the parts of it. So here is an atom from the kit, and it has just one spot or one hole, so it can have one bond, and so that's what's shown behind here. And this is white is usually hydrogen. Red here has two holes, so it can form two bonds, and here's with the bonds in it, so you can see. And red is generally considered to be oxygen, but we can use it for anything that has the same valence. Then here's one of the atoms with three holes, three spots, and according to the map, this beige one is considered boron, and here is just with bonds. These would go off to atoms, bond to atoms, but I'm just showing you the bonds so you can see how the configuration. So you can see this is just a straight, that's not even linear, that's just a bond. Here though, you can see that you'd have an angular or bent geometry. Here's the trigonal planar geometry. Okay, and then I'm going to bring in black is considered carbon, has a valence of 4, so has the tetrahedral shape to it. And then this purple is phosphorus. Move this over. Phosphorus, you can see, has 5 holes. It might be hard to see, so if we put this in, I think this, let's see a little bit better. There's the 5 bonds. That's the trigonal bipyramidal and bipyramidal. And then, and then this has 6. And according to the map, this just indicates sp3d2 shape. They don't even give it the name of an atom. And you can see this is octahedral. So those are all the atoms that are present, and there's different colors of them that they have. I didn't show the blue, and there's green and orange, but we're not going to worry too much about the colors because we're going to be using a lot of atoms that aren't on the map. I know we use selenium, and that's not on the map, but we're really more interested in the valence, the number of bonds these things can have. Okay, along with the atoms, we also have lone pairs. I'm going to show it here. We'll put lone pairs on the central atom. We could put them on the outer atoms too, but we won't because they don't. The lone pairs on the outer atoms don't affect the shape. The other thing is that we have these flexible bonds. The other ones here, these are short. They're just single bonds. They don't move around a lot. Not very flexible, but these are. I have one already here, and then we takes a little effort here, and that's our double bond. And then if we put in another one, it'll be brand new. These are hard. Okay, and that's a triple bond. So that's what these flexible ones are for. So those are the main components of the molecular model kits that we're using. And we'll be using those to build up the structures. And I'm going to show each of the structures, and then you will fill in the blanks in your lab report sheet for each of these. So you'll be given the structure, and I'm going to move it around, and then also show you what the formula is. I'm going to take them right in a row, excluding the first one, which is BF4 minus. That one's already done for you. So we'll start with CCl4. So this is CCl4. The greens are chlorine in the map that they give for the molecular model kit, and that's always the case, that the black is carbon, green is chlorine. So I'll use the appropriate colors when I can. So just turn this over a bit so you can see what you're looking at. So that is your CCl4. Here's the H2Se, so that's selenium in the middle, and you can see it has the 2 lone pairs. Turn it around so you get a good look at it. So that is your H2SE. This would be the TeO2, the tellurium dioxide. Oh, put that in there. So, here is SeO3 2- with one double bond, but remember it has resonance structures, so all these 3 bonds are actually equivalent, so that will give you a better idea of what the molecular geometry should be. This is the PF5, the phosphorus pentafluoride, and fluoride doesn't, or there's no color for fluoride, so I'm just using the white. This is the mercury dibromide. We don't usually work with mercury when we're talking about the Lewis structures, but it has 2 electrons that it can use for bonding, so it ends up being this shape. This is PO3 3-. And so we have a methane that we've replaced 2 of the hydrogens with bromine. So this is dibromomethane, but it would have the same molecular geometry as methane. But just have to have the different color atoms here to indicate that they're different atoms than these here. This is the one that often gets the students. If this were red, then this would be the structure of the sulfate ion. This is yellow for sulfur, red for oxygen. And so this one is called the thiosulfate. Whenever you see something like that where you have that thio in front, it means that an oxygen has been replaced with a sulfur. They're from the same group, so it works the same way. The bonding is the same. So these 2 are sulfur, and these 3 are oxygen. So this is your thiosulfate ion, and that is S2O3 2-. This is the nitrite ion, NO2-. You have the lone pair there and the double bond. And this would have 2 resonance structures, but if you're going to do this with molecular model kits, you have to pick one or the other side for the double bond. And this is the bromine trifluoride. And you can see that it forms that T shape as the 2 lone pairs. And this is why it's good to do these molecular model kits, because a lot of times students don't see the difference here. We always say the lone pairs should go in the equatorial positions rather than the axial. And if you make the mistake and put this, then you get a completely different geometry, and it's the wrong one. So we know that the lone pairs should go on to the equatorial positions. Oops. And there we go. We have the T shape. Here's the ammonium ion, NH4+. So this is a group 5A atom here for the nitrogen, but it's a plus charge, so it loses one of the electrons, so it acts like a group 4A, so it acts like carbon, so it has the same look as the methane, and same structure. This is BrO3-, and there are 2 double bonds and then a single bond, but again, there's going to be resonance structures, so these are all going to be equivalent in length and in their bond angles. Can't show that here with this model, but just think of that when you're considering what the most symmetric shape would be. Oh, another deja vu here. This was the PF5, and this is the ASF5. So phosphorus is in group 5A and arsenic is in group 5A. So one of the nice things about this lab is it shows you there aren't really that many different structures if you have all the outer atoms the same, and if you have all of them the same on the outside, so these are all fluorines, you can replace it with phosphorus or arsenic, and because they're from the same group. And here is ICl3 with its 2 lone pairs. Oops. And here's SEF4 with its, like the geometry that the seesaw. You can see it, that. 1 lone pair. And then the last one, this is xenon tetrafluoride. It has an octahedral electron pair arrangement, and there are 2 lone pairs, and those are going to be across from each other. That's a good look to it right there. You can see the shape of the molecular geometry. And then here's a little, try to get the whole, yeah, there we go. And that's the last one.